All right, I hope you guys are having a good day today. I'm out today hanging out with my kids, and pretty much, I'll be honest, pretty glad I'm not hanging out with you guys today. No, I'm just kidding. I miss you enough. But anyway, let's talk about waves. All right, we just took our test. Hopefully, you guys did okay on that. I'll get the grades up as soon as I can. But today we're going to move in to start talking about waves. And the characteristics and descriptions of waves are what's going to govern a lot of what we're going to talk about in the next few weeks in regard to sound and light, as well as things like earthquakes and water waves, which is what we typically understand when we think about the word waves. I'm going to go as slow as I can on this video, and what I'm doing right now is I'm writing in my own notes as if I were you, and so what you need to do is you need to keep up. Don't be talking to your neighbor, don't be looking at somebody else, don't be flirting with your girlfriend or boyfriend or whoever you want to be your girlfriend or boyfriend. I want you to keep up with these notes as best you can. Here we go. Waves. First of all, a wave can be simply described as a rhythmic disturbance that carries energy through matter or space. A rhythmic disturbance that carries energy through matter or space. Keep in mind, you might want to notice that waves can go through empty space, or there can be matter there. In other words, you can have a wave that goes through a vacuum. Certain types of waves, not all types of waves, will go through a vacuum. But the real important point that you need to remember about this is the fact that waves transfer or carry energy. They do not carry matter, and you might want to circle those words. Waves do not transfer matter. And I'll prove that to you. Think about the last time when you were sitting by the side of a pond or a lake or a river or even just next to a puddle and you throw a rock into the water. Obviously, the rock will cause waves to disperse from the inside toward the outsides of the puddle. But if you think about it, you might remember that those waves did not cause water to move out of the pond or the puddle or the river or whatever it is. In other words, throwing a rock in the middle doesn't transfer that matter from one place to another. The water stays where it was. The only thing that moves toward the outside is the actual wave itself, not water. And I'll explain that more when we get there. Most waves are created by rhythmic vibrations. They could be very slow, they could be very fast. So the frequency can vary, but vibrations are what create most waves, not all the time though. But basically there's two types of waves, and you can see that on your notes. One type is a transverse wave, and the other type is called a compression or a longitudinal wave. And so we're going to talk about both of those very briefly and how they work and what they apply to. So first, a transverse wave. In a transverse wave, basically the particles are going to move perpendicular to the direction that the wave moves. Okay, so for the wave that you're showing down here on the bottom, if the wave itself is moving toward the right, the particles are moving perpendicular to that direction at a 90-degree angle. So instead of moving to the right or to the left, the individual particles are going to move up and down. And I'll show you a video, like illustration, animation, there we go, is the word I'm looking for, to show you a transverse wave and exactly how the particles behave in a transverse wave. Transverse wave looks like what's called a sine curve. You know what that is if you've taken pre-calculus or calculus. But a sine curve is just a special type of graph. It's the graph of sine, if you care about that. And that's what it looks like. That's typically what transverse waves look like. They go up and down like peaks and valleys. Examples of things that use transverse waves are any type of electromagnetic radiation, including radio waves, microwaves, infrared radiation, which is heat, visible light is electromagnetic radiation, ultraviolet light, X-rays, gamma rays, all those things are different frequencies, different types of electromagnetic radiation, and we'll talk about exactly what that is later on in like a week or two. But waves on the water are also examples of transverse waves. The waves are moving outward on the pond, whereas the individual water molecules are moving up and down. And then this sculpture here is a good example of a transverse wave. It looks like this. And you can go to YouTube and find this video on your own. It's a sculpture that is at SMU actually. And all it is simply, if you look closely at each one of these separate particles, it's a long beam that's moving back and forth like a teeter-totter on this center fulcrum here. And each one is moving up and down in a rhythmic pattern. And so it looks like there is something that is moving from left to right, when in actuality nothing is moving from left to right. If you watch each individual particle, it doesn't move. This one goes up and then it comes back down. Move it back to the beginning because they start to get a little wavy. It moves up and comes back down, they move up and come back down, but it certainly looks as if there's a wave that's traveling toward the camera. And it's sort of an optical illusion because there's actually nothing that's traveling toward the camera in terms of matter. Energy in the form of this wave is the only thing that's traveling toward this person standing here. So that's a good example of a transverse wave. So take a minute, if you haven't already, write down some of those examples of transverse waves. Water waves, electromagnetic waves, and that sculpture at SMU is a good example. All right, so this is the animation that I was telling you about earlier. If you'll kind of look from afar back, you can see that these particles, or rather the wave itself, is moving from the left to the right. Right? But the particles themselves, if I follow, for instance, this individual particle here, look at that one, or pick any one out for yourself. If you look at the individual particle, the particles themselves don't move from left to right. They move up and down, but their position remains stable. So you have energy is traveling from the left to the right, but it's interesting because it doesn't take the matter with it as it moves. The energy itself moves because of these rhythmic vibrations that transferred through this bit of matter. Okay, so again, oscillations in a transverse wave. Oscillation means something going back and forth. It's perpendicular to the wave movement. In other words, as the wave energy moves from left to right, the oscillations will go up and down, and that's the third bullet under transverse waves there. If the wave energy moves left to right, then the particles oscillate up and down, or vice versa. And here's another example. If you take a rope and lay it on the ground, all you need to do is bring the rope up and down very quickly, and you can see a wave, a single transverse wave, move across the rope. Obviously, matter in the form of the rope is not moving from left to right because the rope is still held in your hand. If the rope was moving from the left to the right, the rope would physically pull your hand in that direction. All that's moving is a wave, is the energy in the form of a wave in that rope. Doing the wave at a stadium, if you're at a baseball game, football game, whatever it is that you want to do, the wave in a stadium is a really good example of a transverse wave. The wave travels from left to right or right to left, whatever you may have around a stadium, and each individual particle can be considered as each individual person, and each person goes up and then down, up and then down, up and then down. They don't move from left to right with the wave at all. Water waves. This is how water waves work if it's a transverse wave. Water waves are actually quite interesting because if you look at these two that are colored in blue, while they don't change position very much in the x direction, you will see that if they're on the top of the water, they are making a sort of circular motion on the very surface of the wave. And the farther down you get, the less circular the motion gets. But the point is, they undergo no net movement in one direction. So this one at the top is not moving from left to right preferentially. It's moving right and then coming back left because it's moving in a circle. But again, as you can see, the wave moves completely from the left to the right without taking any of the matter with it. As far as parts of a transverse wave, I want you to take a minute and copy down the parts of this wave, and then I'll keep going with the notes real quick. So be copying these on the picture of the wave there that says parts of a transverse wave, and you might also want to go ahead and draw this line right here through the middle of the wave, because that's not drawn in on your notes. Alright, I'm going to go ahead and start explaining these. Remember, it's not 100% necessary that you put these notes on here, but it would help you quite a bit if you put the definition of a node and an antinode on there. So just to start out, let's go ahead and start with the nodes and the antinodes. The antinodes is the point of maximum amplitude, all right? And the amplitude we should probably define in the first place. The amplitude is simply, oh, they're going to come up here with us. Well, let's start with a crest, okay? Maybe we should just scrap all this. Start with the crest, all right? The crest, find a place to write that down. It's simply the top of the wave, at the highest point on the wave. And the trough is very simply the bottom. And that we call that a trough because it's shaped like a trough. It's the very bottom of a wave. Wavelength is symbolized by this Greek letter here, and that's the Greek letter lambda. It looks like an upside down Y, I guess. And the wavelength is simply the distance between successive parts of the wave. For instance, the distance from one crest to the next, or it could be from one trough to the next trough, or it could be from one node to the next node, as long as they're on the same parts of the wave. So that would be from here to here. Could be from one antinode to the next antinode, whatever, as long as they're on the same parts of the wave. The point is, the wavelength is the length of one wave, the distance between successive parts of a wave. So like I said, crest to crest or trough to trough is the easiest way to measure a wavelength. And the amplitude is the distance from this zero line, from this normal resting position, to the top of the crest or to the bottom of the trough. So you could also draw amplitude right here between the zero line and the trough, and that represents the amplitude as well. In other words, the wave rises to the same height that it falls. So that's going to be the amplitude. And those are the basic parts of a transverse wave. You'll see that when we get to compression waves have very much the same anatomy, a lot of the same parts. We'll use the same words, but they'll apply to slightly different things. At least they look a little bit different. Okay, so if you need to pause the video real quick, let the substitute know if you need to write any more of this down, but don't take too much time.